Good evening, everyone. I'm Milton Davis, and welcome to the RDMnet Introduction webinar. And presenting today will be Scott Blair from Megapixel, Sam Kearney from ETC, and I'll be your host starting things up and so forth. Please note that this session will be recorded, so it will be available for rebroadcast at a later time. Quick introduction. Scott, would you like to say a little bit about yourself?
Sure. I'm Scott Blair. I work for Megapixel currently. I've been one of the co-chairs for RDMnet back since the beginning many years ago when we started down this path of creating this new protocol.
And Sam?
Yeah, my name is Sam Kearney. I'm a software engineer at ETC, one of the co-chairs of the RDMnet task group, and at ETC I'm in charge of implementing most of our entertainment network protocols.
Great, thanks guys. And I'm Milton Davis. I'm an ETCP recognized trainer and certificate and work for Linear Design doing mostly DMX and RDM type stuff. So let's go and take a look at this. I know some of you are here for ETCP renewal credit. If you do want renewal credit for this class, you'll be given 3/4 of a point, 0.75 points for renewal credit. And to get that credit, we need you to send an email to the email address shown on the screen now, plugfest@esta.org. You need to include your name, your ETCP certification, and the magic words. What I've been asked to do is there are going to be 2 magic words presented during the course of the presentation. One in the middle of the presentation and one toward the end. If you include those 2 magic words in your email to us, then you'll get the credit. If you don't give us the magic words, you won't get credit. Pretty straight. So that's it for that part. Let's take a look at what this webinar is all about. First is a brief RDM review. What is RDM? Remote Device Management. Exactly why is it that we have RDM in the first place? And then RDMnet capabilities. What happens as we start putting RDM protocol over a network? Operational differences from RDM, because it isn't just a matter of putting RDM messages over Ethernet. There's a bit more involved to it. And associated with that, the system, the components, terminology, all of the tools that go into making RDMnet happen. And then finally, some of the nuts and bolts, how that communication actually works. How does it come together? So with that, am I doing the overview of RDM?
Yes.
I think I am. Okay. What is RDM? Okay. RDM stands for Remote Device Management. It's a protocol that ESTA has put together some time ago now. And it is a bidirectional protocol that works in conjunction with DMX 512. Contrary to popular belief, RDM does not use pins 4 and 5 of the 5-pin XLR connector. It is bidirectional data using pins 1, 2, and 3. So that's an important point to note. What does RDM do? It allows controllers to discover, query, configure DMX 512 devices. Note that RDM is not really a real-time protocol. It's not for show performance capabilities. It's for configuring devices and getting status reports from devices. So as noted here, there's a large defined set of messages or PIDs for common settings, and the RDM protocol is an expandable protocol, and we are always adding new PIDs as new capabilities come to products on the market. Note here, widely supported in many fixtures, devices, splitters. There are a lot of RDM devices out there, and it's growing daily, particularly in the realm of remote configuration. By using RDM, it's faster than getting out the ladder is one of the big selling points for it. Controller support lag behind due to inherent limitations of it being tied to physical DMX 512 links. Okay, RDM has its limits. It is interleaved with DMX, so there's only a certain amount of stuff you can get through there. No standardized or scalable way for controllers to get all this information back from third-party gateways. So RDM has definitely got its place. It supports really quite large systems. But as we start moving into more 21st century products, RDM is sort of the last mile connection. And from there, we are wanting to get it onto a network. So that's where RDMnet comes into play. And with that said, I'll turn it over to Scott and Sam to say, what is RDMnet, and pick it up from there.
So I think the slide kind of ties it all together, where RDMnet fits in the universe here. So we first started off with DMX 512, which was later standardized under ANSI as E1.11. The revised version that we all kind of know and love today was released back in 2008. So DMX 512 is basically unidirectional control data, slot information that operates over RS-485. We then later, we added RDM originally in 2006. You can see that we revised it in 2010 there. And RDM then added a component to allow us to do bidirectional communication. So now, for the first time, the console could request information back from the devices. And then this allowed us to do things like setting the DMX address on the device, getting basic information about what the products are that are connected to the DMX 512 link, and status information back. But this was all done over RS-485. So in 2009 or so, we added E131, which is streaming ACN. This allowed us to send control data, DMX 512 packets, over a network. So we basically would package up the DMX 512 frames, and then package them up and send them over a network. So we can now have many universes of DMX 512 all running over Ethernet. But we lacked the ability then of getting all of the feedback information back. We did not have a standardized way of getting all of the RDM data that comes back to a gateway, getting that back all the way back to a console. So now we have RDMnet, which allows us to pull all this information back. So it gives us the ability to now do fully bidirectional configuration and monitoring over Ethernet, both for native devices, native E131 devices, but also then for going through a gateway and speaking to DMX 512 RDM devices, as Milton said, kind of the last mile. Went to the next slide. All right, so what does RDMnet let us do? So first of all, as I said, it extends the functionality beyond the limits that we had of DMX 512 onto an Ethernet network. So again, before, basically RDM is great if you have a small system. In a larger system, your point of control from an RDM point of view was typically a gateway or a node, which generates all the control information. So you then had to, in order to build a full RDM system, you had to have a console that used nodes typically from the same manufacturer, so they had a proprietary way of pulling back all of the RDM data from the gateway back to the console. Or you would use typically the RDM management functionality that was within the node system itself. But again, this required you to typically have nodes or gateways that all come from the same manufacturer. So with RDMnet, it now removes this limitation. So we have this interoperability across the network between all different manufacturers using this new protocol. It allows for large-scale system monitoring and configuration. So we're not just limited to what comes out of a physical DMX 512 cable anymore. As I said, we're extending it back so I can have a much larger system than what we could before. We're scalable to a large number of devices with RDMnet, well over 10,000. The limit is really the network. As you scale up larger and larger, your limitation is really just network and processing. So if you have a very big network, you can scale it even larger, using the right type of processing equipment and the right type of network. You'll be able to scale even way above that. One of the other major benefits that RDMnet gives us is finally we can have multiple clients to configure and monitor devices together on a network. We're not limited to, with RDM, as with DMX512, you can only have one controller driving the wire at a time. So with RDM, you typically only have one controller that is communicating with the devices to pull the information back. Now with RDMnet, just like anything, on a network, we can have lots of clients out there. And in the case of clients will be, consoles, but also we can have, tablets and cell phones, smartphones that can have applications running on them that can interact with your system as well. So it truly does open this up to kind of a modern workflow. But one of the key things is when we've got multiple clients, and this is one of the toughest problems we had to solve with RDMnet, is when you have multiple clients that are changing settings on a fixture or pulling status information back, you need everybody to be in sync. You can't have one person making a change and another person doesn't realize the change has been made. So one of the key things that took a lot of effort to solve in the architecture was how to make sure that all of the clients have all of the data all the time, that everybody is in sync. So if Sam is on his lighting console and he changes the start address of a fixture, and I'm on a tablet, up on stage or in a lift, I can see that he's changed the DMX address. Everything is in sync, so you don't end up with any kind of problems of people having different information. Everybody would have all the same information at the same time. Another big feature of RDMnet is the use of scopes, and we'll talk more about what scopes are later. But in a nutshell, what they are is they're a way for us to partition a system into smaller subsets of a system. So typically if I have a big performing arts center and I've got multiple theaters, maybe I have a main stage, a proscenium theater, and a black box, and they're all shared, same network in the building, but I need to be able to partition the system and make sure that the black box theater doesn't, control something in the other performance space. It's also very common in touring rigs and other things where you need to have a touring system able to grab control of the lights in the facility, front of house lights or house lights in a facility, and drive them as well. So scopes allow us to kind of partition things because in the end, typically everything ends up on one big giant network anyway, but you don't want you want to have some granularity in how you interact with the devices on the network so that everybody doesn't see everything all the time. You can provide the appropriate level of visibility. Another big benefit over RDM is with RDMnet, it gives us event notification without requiring constant polling. So if you're familiar with RDM, you know that because you can only have one device, one master controller talking on the DMX512 bus at a time, that devices, if they have status information or a setting has changed on the front panel and they want to report that back to the controller, they have to wait for the controller to poll for that information. And it could be in a big RDM system, it can take a while for all that polling to happen. So with the RDMnet, once you're on the Ethernet side of the gateway, all of this event notification can happen back to the controllers without requiring any kind of polling. Because we're on Ethernet now, things can talk asynchronously back to the controllers. We don't have to wait for that dead time in the physical wire to be able to talk back without having a collision. So this is a big thing. It allows us to offload then the processing of all of the polling of messages on the RDM side. That could all be offloaded to the gateways, and when gateways get the information from RDM devices, they could just send it back up to the controllers at any time without having to wait to be polled. So this is another big benefit as you start getting scalability into larger and larger systems. The last thing I'll talk about on this slide here is that we've provided common standardized PIDs or parameter messages, configuration messages for gateways. that allow us to now configure all of the common settings that you would have on a DMX512 to SAC into DMX512 gateway. In the past, there really was no way of setting all this stuff remotely across different vendors. So we'll talk about that a little bit more in the next slide here. So in E137-7, it's a separate companion document to the RDMnet document. We've defined a suite of messages that allow for the configuration and the management of these gateways, again, regardless of the vendor. So now we have the ability to assign universes to endpoints or ports. And you're going to see some references to endpoints here as we go through the presentation. For the moment, we'll explain the subtleties a bit more of why we have a different term here. But for now, as we're talking about it, when you see the word endpoint, because I want to use the proper terminology, but just think of them as ports. So on a gateway, you've got a number of ports on the back of it that are, each one of those is aligned to our universe of DMX512 and RDM. So now we have messages, standardized messages, that allow us to configure and assign universes to those ports, to those endpoints. I can identify, there's a method for identifying endpoints, so I can tell which jack it is that's on the back of the gateway. I can have it flash an LED or do a specific action, so I can tell which one I'm plugged into. I can assign labels to the endpoint, so I can put a label of, this is going to the first electric or the second electric. So again, useful functional labels for the user. I can do things like setting the endpoint mode of that gateway. So I can tell it if that port is an input port or an output port, if it's going to transmit DMX512 or if it's going to receive DMX512 from another device. I can also disable it if I want. Another interesting one here is disabling RDM traffic. Well, we're all about RDM here. Why would we want to turn it off? A common problem we run into with a lot of non-compliant DMX512 devices is that they do not properly check the start code. So there are times where you do have to disable RDM, not because RDM is causing a problem, but because you've got some devices that aren't actually compliant to the DMX512 standard. So we've provided a standardized mechanism where you can do that on a given port or a given endpoint. Also, getting the device list and managing discovery. So I can see what all is connected to the gateway. And then finally, as we've talked about, managing how queued messages and status messages get collected back. Some operational differences here from RDM. As we said, it allows for an arbitrary number of controllers that can operate on the network at the same time. I'm not just limited to a single controller now, as I was with RDM. I can have the native RDMnet devices, as I mentioned. They can asynchronously report all the data back to the controllers. They don't have to wait to be queried on. The gateways handle the discovery of all of the RDM devices that are connected to them on a given endpoint or port, and they report the device list back to the controllers. The gateways, they do the collection of all of the queued and status messages and forward those back up to the network. And the gateways then also do the completion of ACK overflow messages. You know RDM a little bit deeper down. Then we have basically a mechanism for sending very large messages back where you kind of page through the response in multiple packets. It used to be that the controller had to do kind of all of this paging, but as you get into a large network, it's not really practical. So we've offloaded that now to the gateway where it handles all of that for kind of the last mile. So let's talk about RDMnet system components. So the first two of these are pretty recognizable. So you've got controller. We all associate a controller as typically being a lighting console or a house light controller. It can also now be an application running on a smartphone or tablet that interfaces with the rest of your system like an RTU. Devices are obviously a dimmer rack or a moving light. Again, things we're all very familiar with, but there's a new item here. There's a new component that will be very new to you. It's called a broker. And what the broker does is it handles all of the communication between the controllers and the devices. And we'll get into more detail later about how the brokers work, but basically this is the key component that allows us to synchronize everything between all the controllers. So all of the devices and the controllers, they all communicate through a broker. And then that broker is what keeps everybody in sync and makes sure everybody has the same data. So let's look at an example system, RDMnet system diagram here. So you can see that I've got a lighting console here, and you can see the lighting console, it has both the controller and the broker inside of it. And that's what you will commonly see in vast majority of the systems, unless you're getting up into a Disney's theme park level scale of system where you're going to need to have a separate broker. Typically, your broker is going to be just a component that's running in your lighting console. Much the same way as a DHCP server is a component that runs inside of a network switch or inside of your router at home. It's just a function of the lighting console most of the time, but it is a separate component that is running inside there. And then, as you can see, we have a couple DMX gateways there to talk to some actual DMX 512 RDM fixtures. And we have a couple of networks fixtures that are taking E131 natively. But then you can see in blue my other controllers. I've got a mobile RFU app running on a tablet. I've got a laptop running some configuration software, obviously the console, and then an architectural lighting panel. And so these all then can act. I can have these 4 controllers all interacting with RDMnet and being able to see all the status information and access configuration on this system at the same time. I'm not just limited to the one lighting console like I was in the past. All right, so we talked a little bit about scopes just very briefly. So what are RDMnet scopes? As I mentioned, they allow us to partition a common network into multiple independent systems. So some good examples of where this comes up, where we need to do this are, as I mentioned, you've got multiple performance spaces in a single venue. You also could have your theatrical lighting versus your front of house architectural lighting that you need to isolate into different systems. But it's also common on a big show. I see this all the time, where you'll have 3 or 4 different lighting consoles, out front of house, all programming different parts of the same show. So I might have a moving light console and a theatrical console and a media server console that are all programming it. But now they can all, in many cases, they're all feeding into a large streaming ACN network. So they're sharing all of the infrastructure, but they each have specific devices and things they're controlling. So this then allows us to still have them all share the same network, but devices can be configured to be within a scope, so each console only sees and accesses the devices it's responsible for. Another example is a touring rig versus a house rig. This is actually one of the great strawmans we use during a lot of the development of how to make scopes work and how they work with the system, because I may have a house system in my theater, but I've got a touring show coming through, and they're going to bring their own lighting console, and they're going to bring all of their lights that go on stage. But they still need to interface into the system in the building to be able to control the lights that are at front of house and the box booms and maybe even the house lights. So they need to be able to interact with that without repatching the entire facility. So in this case, they might operate on different scopes, but the console, the touring console, could then have access to the scope for the facility itself. So what are the rules of RDMnet scopes? The main thing is that as you can tell from some of the discussion, the controllers and devices, they are only allowed to communicate with other devices that are in the same scope. So communication does not cross between scope boundaries. The controllers can operate across multiple scopes, though. So in my example of the touring rig versus the house rig, facility rig, I can have a controller that can operate in both scopes. Might also be important in a theater, again, for the lighting console to be in the scope of the stage lighting system, but also be able to control the house lights as well, which might be a different scope. Each scope has a unique name to identify it. So this name is how we partition and define a scope. Another important rule is that basically new products or products have been factory defaulted. There is a defined default scope. So this way, the out-of-box behavior is interoperable. So if everybody follows the standard, if I get a whole collection of different devices and they're all just operating in the default scope, I don't need to, and I don't have a big system I need to partition. Everything should just operate and communicate out of the box together without doing any configuration of the scopes. And that's probably the way 75% of the systems out there will work. They will probably just live in the default scope, and that's fine. But the power of scopes allows us to really have some important scalability that we need for the bigger shows. So if we look at the next slide here, we can see an example of a scoped RDMnet system. This is a very simple example, but kind of as I was saying, I've got scope 1 has a lighting console and theatrical fixtures for the auditorium itself, and then scope 2 is the architectural fixtures and then the lobby lighting control panel. And shifting gears a little bit here, we're going to talk a little bit about LLRP. LLRP is it's a very important kind of a sub-protocol within RDMnet. It's a separate component protocol that we developed. The purpose of it is to allow you to access and change the configuration for a device that is assigned the wrong scope. So if I have something I don't know what the scope is set to, and I don't want to have to get the lift out there to set the scope to be able to access it, I want to be able to do that remotely. And it's a common problem with IP addressing too. If anybody out there has ever used a DL2 or a DL3 digital light from high-end back in the day, you might have been very frustrated that you couldn't set the static IP address on it. There was a great reason for that, and that was because we had the philosophy of you should be able to just hang your rig, fly it up in the air, and no matter what anything is set to, you should be able to, as long as you plug the network in correctly, you should be able to configure everything from the ground. You shouldn't have to worry about setting IP addresses or doing any of that from the ground, because odds are it'll end up in the air, it'll be wrong, you'll have to make a change, and it'll be very difficult to troubleshoot the network up in the air. But the reality is we've seen far too many products out there these days. Moving lights all have the ability to set static IP addresses. In some cases, they may require you to set static IP addresses. So it was really important that we find a way for dealing with changing IP addressing from the ground, no matter what it's set to, without having any knowledge of what network it was set to. If it was completely misaddressed, it doesn't matter. We have a way of doing that now. So LLRP, it stands for Low Level Recovery Protocol. It uses multicast and allows us to discover one device to discover and communicate with the other, even if they don't have valid IP settings. Multicast is what we use in streaming ACN. So with streaming ACN, it doesn't matter what your IP address is. You can have some devices as a 192.168.x.y network, and you can have other things in the 10.0.0.0 network or a 169.254 network. It doesn't matter. As long as it has an IP address, it doesn't matter that it's in the same network. They all can communicate. But multicast doesn't scale. It doesn't scale to the level, and it doesn't scale in the way that we needed for RDMnet. It's great for a one-to-many, but it didn't work well for the many-to-one. So we used multicast with LLRP to allow us to access these devices and get some basic information back and do things to have messages to change the IP address settings and to change the scope regardless of what the network is set to. But that's it. So LLRP, we allow for just enough of the RDMnet communication, just enough messages that allows us to get a device connected to RDMnet so it can run the full RDMnet protocol. And that's kind of the limit and scope of LLRP, but it's a super powerful component of RDMnet because it allows us now to solve a problem that there really was not a good solution for out there, certainly not across multiple vendors. So now I have a standardized way of doing that. So in configuring an RDMnet system, really the only two things you have to do is your IP addressing and setting scopes. So you will have to have in an RDMnet system a valid IP address that is in the same network as everything else. So you will have to have your full TCP communication between the device and the broker or the controller. And you can do that by any means you want. That could be a static address, it could be DHCP, it can be auto IP. Generally speaking, most of the time we recommend using auto IP or DHCP because as you get into a large lighting system with a bunch of stuff up in the air, it just becomes a bookkeeping nightmare to keep track of all of your static IP addresses, and it's the easiest thing to mess up. And once you start having multiple things set to the same IP, it really starts to mess with the network. So, and it can be a pain to troubleshoot. So this is why we like to recommend auto IP or DHCP, but with LLRP, you can do whatever you want now. And then the only other item we have to do is set the scope. And as we said, in a small system, they can pretty much just leave this as a default. All right, moving on to endpoints now. So an endpoint is basically, we refer to it as an attachment point that allows the configuration of an E131 universe. The reason we change the term here from the commonly known term of port to endpoint is because a port is often viewed as a physical thing. It's used to mean a lot of things, but it's often viewed as a physical port on the back of a DMX512 streaming ACN gateway. But you can also have native devices that take multiple universes of DMX or multiple universes of streaming ACN. So I can have a media server that takes 5 universes of data, and I need to patch each of those 5 universes of data. So I would then, that media server would then expose 5 endpoints to do that. Basically, it can consume 5 universes of DMX512 data, so I have 5 patch points or endpoints to do that with. An endpoint can be physical or virtual. So as I was saying here, a physical endpoint corresponds then to real-world DMX512 interface hardware. It is the physical XLR jack on the back of the gateway. But a virtual endpoint corresponds to logical entities within the device. So again, a moving light or a media server taking E131 and E133 natively, that would be considered a virtual endpoint. And at this point, I'm going to hand it over to Sam to go through a little bit more of how things actually work.
But before Sam does that, Milton's going to jump in again real quickly here. And for those of you who are doing ETCP credit, the first magic word is Plugfest, Plugfest. While we're here in Dallas, where we're presenting from tonight, we are running the ESTA Plugfest, where we are putting different manufacturers' protocols together and seeing that things actually work in the real world together. So that's another reason all of us are gathered here right now is for the Plugfest. So that's one of the magic words is Plugfest. Also, as we continue on, if you do have questions for the presenters, please put those questions in the chat window on your screen, and we will. And sorry.
The Q&A panel.
The Q&A panel. Thank you. So there is a Q&A panel, and put your questions in there, and we'll do our best to answer them. Thanks for the interrupt, and Sam, on to you.
All right, thank you, Milton, and thank you, Scott. So what we're going to do now is give an overview of kind of some of the technical building blocks that go into the RDMnet ecosystem and do a slightly deeper dive into each one of them and how they work. So basically what makes up RDMnet is a discovery method for which we use MDNS or DNS-SD, also known as Bonjour. We have a protocol called RDM packet transport, which is for sending RDM messages on the network. We have a protocol called extensible packet transport, which is for manufacturer-specific or future protocols, thus the extensibility. And then we have the protocol called low-level recovery protocol, as Scott mentioned, kind of a get-out-of-jail protocol for misconfigured IP addresses and scopes on the network. And then we have the set of defined configuration messages that interoperable devices between manufacturers can use to configure each other. Most of these are defined in E137-7, which is a companion standard to E133, although some of them are defined in the RDMnet standard itself. So this is just kind of a stack-up diagram of all of the message types that exist within RDMnet. And I'm not going to go deep into any of these message types. I'm just putting this up on the screen to illustrate that all of these message types are neatly gathered within the PDU structure that's defined by the ACN protocol family. So if anyone's ever done any deeper looking into how streaming ACN works, you'll notice that the top two rows of this protocol stack are basically shared with streaming ACN messages. And the benefit of this is that it's a familiar interface for developers, and it allows some shared parsing code for people who have already written implementations of streaming ACN that transfers nicely to RDMnet messages. So let's get into RDM packet transport, which is kind of the bread and butter of RDMnet, because it is what transfers RDM packets on the network, and just talk about how it works. So if you're familiar with how RDM works, just as a review, in RDM, controllers initiate communication by sending an RDM command to a responder, and then upon receiving this RDM command, the responder sends an RDM response back to the controller. All the communication is initiated by the controller, and then it allows the responder to respond. This communication takes place over the RS-485 physical link that makes up DMX. In RDMnet, the process looks very similar. There's just one added step. There's a component called a broker in between. So to initiate an RDM command transaction in RDMnet, a controller will send an RDM command to the broker, which then forwards that RDM command onto the device. Upon receiving this command, the device generates a response and sends the response back to the broker, which then routes it back to the controller. The broker uses some addressing information that's present in the RDM command to determine the correct device and controller to send these messages to. And all of these messages are sent over TCP for reliable communication between controllers, brokers, and devices. This is by contrast to protocols like streaming ACN and RDMnet, which use UDP for communication. So these three components are the three core components of RDMnet that Scott touched on earlier. So a controller originates RDM commands over IP and receives responses. A device receives commands over IP and generates responses. And then the broker, which is kind of the core component in the middle, is responsible for routing all of the RDM commands and responses between controllers and devices and maintaining the overall state of the system. It's important to realize that at least one of each of these roles is necessary to build a functional RDMnet system. And in particular, you should note that there's no communication possible between controllers and devices in RDMnet without a broker being present. So you really have to have at least one of each of these devices in order for an RDMnet system to work. So I just want to take a quick digression here to explore the need for the broker, because some might be a little bit confused as to why this kind of middleman is necessary for communication between controllers and devices, and why they can't just send directly back and forth between each other. The broker actually adds a lot of value to RDMnet in many different ways. The first of these ways is the ability to build a multi-controller system. Right, so in RDM, as Scott mentioned, there's only one controller possible in a system. In RDMnet, you can have as many controllers as you want, and the broker allows this. The way it allows it is by ensuring that each controller always has an up-to-date view of the state of the system. So just for example, let's say one controller sends a set command to a device by means of the broker. The side effect of a set command is that some sort of state or data is changed on the device. Maybe the DMX start address has changed, the classic example of RDM. So now all of the other controllers in the system need to know that that device has a different DMX start address, not just the controller that sent the message. Fortunately, when the device sends the response back to the broker understands this and routes the set work command response back to every controller in the system. So even the controllers that didn't originate the message now understand that something has changed on that device without their knowledge, and they can update their view of the state of the RDMnet system. The other thing that, one of the other things that a broker adds to an RDMnet system is scalability. So in RDMnet, each controller and device only needs enough resources to maintain its connection to a broker. In other words, it only needs to worry about one TCP connection, which is its connection to a broker. This is by contrast to a system without a broker, in which each controller would need to have an individual connection to each device, and the number of those connections would scale with the size of the system. In this case, the responsibility for having the resources to deal with a large system falls completely to the broker. So if you have a broker that's advanced enough and running on good enough hardware, you don't need to worry about the technical capabilities of any of the other components of the system. This makes RDMnet inherently scalable to large systems. And the third value that the broker adds to the RDMnet system is that it adds simplicity. So this is more from the perspective of somebody who wants to implement a piece of equipment that uses RDMnet. If you are implementing, for example, a controller or a device, the set of logical steps that that software needs to take upon startup is very simple. Really, in both cases, you just need to discover a broker and connect to it using TCP. If you're a controller, you ask the broker for a device list, and you use that to present that information to the user, and then you start sending RDM commands to get data and change data. If you are a device, like a gateway or a native network fixture, the process is even simpler. You just have to open that TCP connection and start listening for RDM commands. There's no tracking of controllers or subscriptions to different data that the device or controller need to worry about. That's all the responsibility of the broker. So if a reliable and functional broker implementation is available somewhere for people to include in their products, that means that RDMnet is very easy for manufacturers to adopt because they just have to use this simple logic of a controller and a device. So just a little bit of a deeper dive into some of the broker setups that, the system setups that Scott was mentioning earlier. In the example where the controller and broker both live inside a lighting console, what would typically happen is that the controller would be the graphical software that the user uses for lighting control, like the lighting console software that you're all familiar with. The broker would probably be some sort of system service or daemon that's running in the background on the lighting console, and the controller would connect to it via TCP through the local network stack. And then the broker maintains all of the external connections to each of the devices in the system. It also maintains external connections to other controllers like the mobile apps or architectural panels. In a more complex setup, you might find a broker on its own on some dedicated server hardware that might have some higher resources and is able to maintain the state of the entire system. In this case, all the connections would be external. You would have a broker sitting on a server somewhere in a closet, and a lighting console, architectural controller, mobile app, all of those things would discover and connect to the broker, and the broker would also maintain the connections to all the devices and maintain a device list that the controllers could query.
So one of the questions that we've had is asking from people online is asking if a broker is a physical device or if it is a piece of software that can be running on something. So the answer is it's a software process. So as we said, typically it'll be built into a controller, into a console, but it can also be it can be a separate thing. It could be a completely separate device, physical device, but it could also be a software component that if you don't have a console that supports RDMnet, yet it could be a software process that runs on your tablet.
Yeah.
So the broker can really live anywhere. The key is you just have one of them in your system.
Yeah, exactly. And on this slide, I was really trying to illustrate that the lighting console is basically one machine, and the controller and broker are two different software processes that are running on that machine. As opposed to this one where the broker is its own component. But really, like Scott said, the broker is just a software component that can be moved from device to device, or you might find on any number of devices. So brokers go hand in hand with the concept of scopes in RDMnet. Each scope has its own broker. So this makes the setup of a large system pretty simple. All you need to know is that every scope has to have a broker associated with it. In this case, I've illustrated two scopes, one called main theater and one called black box. This is for a multi-venue or a multi-space venue. Each of the spaces has its own broker. It has some set of controllers and devices. Maybe each one has its own lighting console. Each one has its own gateways and fixtures that don't need to be aware of each other. And then outside of each space, you have the architectural controller for the entire venue that needs to be aware of what's going on in every space so that somebody can see the state of the entire system. And because, as we mentioned before, in RDMnet, controllers can participate in multiple scopes simultaneously, this is possible for the architectural controller to discover and communicate with each of those discrete systems. Another thing that's important to realize about the broker is that the broker is transparent to most users. The RDMnet protocol is designed so that most users don't need to interact directly with a broker to use configuration software. So in well-designed software components, the user won't have to go through a step of, oh, make sure the broker is on before you do anything else. That should just happen automatically in the background. So really it should just look like if I connect a controller and several RDMnet capable devices to a system, everything will just work. What facilitates this is like Scott said, everything ships from the factory set to a default scope. So when you bring a set of new equipment online together, including a broker, everything will be set to the default scope, discover each other, connect to each other, and just work. Another thing that facilitates this is that broker conflicts are resolved automatically. So if you take multiple pieces of equipment that have brokers running on them and bring them up in the same network, the first broker wins, and the second broker will enter a standby mode until it discovers that no other brokers are present on the system. It should be very rare for a user to have to resolve conflicts between brokers. Of course, if you're setting up a large multi-scope system where you're coming up with different names for scopes, or something goes wrong, you will have to be aware of brokers because you will have to set up the scopes on each one. But like Scott said, we anticipate this to be kind of a more advanced usage that a minority of cases will use. And in most operations, the broker should just kind of be in the background and just work. This is how RDMnet works in the presence of the gateway. Like we said, RDMnet standardizes the behavior of gateways. So an RDMnet-capable gateway will present itself as a device. That's kind of a gateway is kind of a special case of a device in RDMnet. And it adds another step to the transmission of RDM commands and responses. So like we said before, the controller will send the command to a broker, which then forwards that command to the gateway. The gateway translates the command to normal RDM, sent over the DMX wire. That gets sent to the responder, which responds to it. And then the gateway initiates network communication back to the broker. It packages that response in a form suitable for transmission on the network, sends it back to the broker, which then routes it back to the controller. One thing that Scott mentioned before is that gateways can automatically collect queued messages from RDM responders. This is the way that an RDMnet system can be notified of an asynchronous state update on an RDM responder. When I say asynchronous, I just mean it was initiated from somewhere else, outside of the scope of the RDMnet system. Maybe a manufacturer used their own configuration software, or someone used a manufacturer-specific configuration software to configure an RDM responder, or maybe someone got up on a ladder and went onto the panel of the device and changed some setting there. When that happens, the RDM responder will queue a message that indicates that something changed. The gateway will fetch that message using a getQueuedMessage command in RDM, and it will get that message back from the responder. And then the gateway asynchronously, like unsolicited, sends that RDM response back to the broker. Because none of the controllers on the network initiated this transaction, it was kind of initiated out of band of RDMnet. The broker knows that it then needs to send that response to all controllers in the system. so that every controller is immediately notified when some sort of state changes on an RDM responder. So one of the components of RDMnet is a network discovery method. This is what makes it so that you can, your devices can all discover and talk to each other without having to type in any IP addresses or anything like that. In RDMnet, there's only one thing that needs to be discovered, and that's the broker. So all controllers and devices discover the broker and connect to it. The broker discovery is performed via something called DNS service discovery. This is also known as Bonjour. It's a standardized protocol for discovery. It's the most popular implementation is by Apple for discovery between their music software and also printers and other things on the network. We've leveraged this industry standard protocol for use in RDMnet. And once a broker is discovered by controllers and devices, other controllers and devices can be found by just querying the broker for a list of what's out there. So the broker maintains a constant list of all controllers and devices that are connected to it that can then be fetched from it by any of them at any time.
One of the big benefits of using DNS-SD is that because it's a standard that's very widely adopted across many different industries, it exists in a lot of operating systems already. The support is already built in, baked into the operating system, so you don't have to write the code for it. It already exists. Or there's plenty of libraries out there to do it for you, so it's widely available.
Yep, especially the big three. If you talk about Windows, Mac, and Linux, there are standard kind of reference implementations for all of those that you can get, or sometimes they're just already running on every system. So just a quick overview of what DNS service discovery is. So some of you might be familiar with traditional DNS, the domain name service. What DNS does is it translates a domain name to a network address. This is one of the building block protocols of the internet. So it's what happens when you type in something like www.google.com into your browser. The first thing that will happen is a DNS query which translates that name into an IP address, which tells your browser what server to connect to. DNS service discovery is pretty similar, and the only difference is that it translates a service name to a domain name. So a service in this case means anything that provides a service that you need. In this case, our service is RDMnet, right? So something querying DNS service discovery will say, is there anything out there that provides the RDMnet service? And it may get one or more what are called service instances back. In this case, each service instance will be an RDMnet broker. This is what I meant by everything discovers the broker, right? And then the second step of DNS service discovery is to choose one of those service instances, and then you can translate that into an IP address, just like in traditional DNS. People who are familiar with DNS might wonder if they need a DNS server to accomplish DNS, and if this means they need to stand up a DNS server on their lighting network now. And the answer is no, you don't. DNS service discovery can operate over MDNS, or multicast DNS. Which is a version of the domain name service that uses multicast queries and responses in place of a DNS server. And RDMnet standard requires brokers to respond to DNS-SD queries over multicast DNS. And as an added bonus, DNS-SD can also be performed with a traditional DNS server. So if you don't trust multicast DNS, or you want to operate in a wider network setup that requires a static DNS server, you can use it that way as well. But multicast DNS makes things really easy. A lot of things it's part of Bonjour, so a lot of things also implement that. It's discovering a broker using multicast DNS is really simple. It's kind of a four-step process, really. The controller just makes a multicast query and says, are there any brokers out there for whatever scope the controller's been configured to operate on? In this case, main theater. The broker will respond when it gets this multicast query saying, yes, I'm on the scope main theater and I'm calling myself main theater broker. It comes up with what's called an instance name for itself. And then there's another query response step after that where the controller says, where can I reach you, main theater broker? And the broker responds with an IP address and port that it can be reached with. And from then on, it's really easy. You just open the TCP connection and go to town. And then here's just a slightly deeper dive into how LLRP works, the low-level recovery protocol. So as we said before, low-level recovery protocol facilitates the recovery of misconfigured RDMnet devices. And to serve this goal, all messages are sent via multicast UDP. And this means that the messages can be received even by devices with completely separate IP settings, as Scott mentioned before. LLRP also uses the RDM command format to configure devices, which adds to familiarity for people who are implementing it. In LLRP, devices that initiate discovery and send commands are called managers, and things that receive commands and send responses are called targets. And the only reason for this different nomenclature is just to avoid a bunch of overloaded words with RDMnet communication and make it clear when you're talking about LLRP and when you're talking about RDMnet. But the concepts are really quite similar to controllers and devices. Manager is analogous to a controller, and a target is analogous to a device. So discovery in LLRP basically works like this. A manager will send a message called a probe request, which is sent to a multicast address. Any LLRP targets out there who are interested in operating on LLRP will be listening on that multicast address, and they'll both send what's called a probe reply, which the manager will receive. So the manager just receives all these probe replies and builds a list of all the targets that are out there. Once the manager has its list of targets, it can address each one of them individually with RDM commands. So in this case, it can send an RDM set command. The parameter here is IPv4 static address, which is defined in the standard E137-2. And the target will send back a set response after getting that request saying, yes, I acknowledge my IP address has changed. It's really quite simple. So this is basically the list of RDM commands that are allowed over LLRP. As Scott mentioned earlier, because LLRP, the way LLRP is designed using multicast queries and responses, it doesn't have the same scalability as RDMnet. So it's really just meant as a bootstrapping or recovery protocol that contains just enough functionality to get your RDMnet communication working again. It's kind of the last piece of the puzzle to set up an RDMnet system automatically without having to type in a single IP address, basically. So because of that, these are the list of RDM commands that are allowed to be sent. It's just basic commands to get information about a device, to get and set information about its IP settings, and to get and set information about its RDMnet settings.
And no more. You're limited to just these messages for LLRP because LLRP it is not designed to be a scalable protocol. It's basically a bootstrapping recovery protocol. So we intentionally limited LLRP to just the most basic limited set of messages that we could to get it functioning onto a full RDMnet network where you can enjoy all the other benefits of the scalability that it provides.
Yep. And the last piece of the puzzle as to how LLRP serves RDMnet is that every RDMnet component, controllers, devices, and brokers are required to function as LLRP targets. So because the standard requires this, you can be confident that if someone says that their equipment implements RDMnet, they'll be able to take advantage of this kind of zero configuration functionality, including LLRP, to get the system up and running in a very user-friendly way. So that basically brings us to the end of the dive into the RDMnet's technical elements. I just wanted to add that RDMnet, as Scott said, is truly the last piece of our control and configuration puzzle. And with it being published, we're moving towards a more interoperable future. And that's one of the primary goals of ESTA's Technical Standards Program. So this one, Milton, if you want to take.
Sure. So you got sort of an idea of what RDMnet is all about. And as always comes up with any standards, particularly ones that aren't quite published, like RDMnet, as shown on this slide. We're in the final stages of publication of RDMnet. We're anticipating RDMnet being a released standard. I'm going to make my best guess within 1 to 2 months. And I'm looking around the room of the experts that are with me and seeing if they're nodding their heads, and I think we're in a general agreement.
I think the important thing is to note is that the standard itself is done. There's no changes that have been happening. It's gone through all of the the normal approvals it needs to go through. We are just waiting for kind of the rubber stamp from ANSI at this point before it can be published. So the standard is effectively done. It's just going through the rubber stamping process.
Yep. So
I can talk briefly about our open source.
yeah, please do.
Yeah. So ETC is currently developing an open source implementation of RDMnet. It's actually available right now on GitHub. So it's an implementation in C and some C++ for Windows, Mac, Linux, and several embedded platforms. I think that the most important part of the open source implementation is the broker, which we currently have in a pretty good working state. And when it's done, it's licensed under a permissive open source license, which will allow any developer of commercial entertainment products to take it, build it, and drop it in with their products however they want without paying any royalties or any attribution. So we've done this because we want to facilitate adoption of RDMnet in the industry.
And the really important and good part about this is the broker. Many people may be writing obviously their own controller implementations, their own device implementations, but the broker is kind of the important piece of glue that binds it all together. And it's a burden for everybody to have to go out and write a broker. So having an open source available broker that everybody can immediately start building upon, I think is a huge benefit.
Right. So in addition to ETC open source, Artistic License out of the UK is also doing something a little similar. They have a final draft. The important thing to remember with all of this is that while the standard is not officially released, there are not going to be any technical changes about the standard as it is released. It's done. It's in the box, and it's just going through procedural things at this point. So, how do we get it? Well, that's up to you. As you've seen some of the benefits through this presentation, you just need to ask manufacturers to support it. Follow the money, as we always say. If you need a feature to make your world work, then ask the manufacturers for it. Demand it. Make it part of your requirements, your specs. Because if there's something to be benefited by the manufacturer by selling equipment with this protocol, it will get delivered to you one way or another. So that's pretty much what we have for here. It's time for me to deliver the second magic word for those of you doing certification renewal points. The second magic word is unicorn. UNICORN, unicorn. So again, please, if you are doing recertification credits, send your email to plugfest@esta.org and include your name, your ETCP certification number, and the two magic words. I also want to take just a quick moment to recognize Jason Potter, who's been part of this. He has been our web guru. He's been running this entire webinar, and he's the one who's been answering your questions online, and I think there have been a few, yes?
And some of the answers are correct.
So we do have a few minutes, so wanted to see if there are any questions from online or any questions from anyone in the room who's here live.
We'll give everybody a moment to type. Any questions from in the room from anybody? Yes.
So something just came up when we had multiple messages hitting the broker as a controller, a bunch of controllers sending, say, a set command through the broker. It gets to the device eventually, comes back, and then the broker broadcasts the results of that set. How does that handle, I guess, concurrency and multiple sets just at the same time? Or the broker should just handle that in a queue?
Absolutely.
And repeat the question.
Yeah. So the question was, when multiple set commands are going through the broker and set responses are coming back and being broadcast to controllers, how does the broker handle concurrency? So, for example, if there are two sets maybe on the same property on the device from different controllers at almost the same time, what should happen then? And the answer is the standard doesn't actually make a mandate beyond the fact that those things need to be serialized.
So you just order it.
Yes, so it is the responsibility of the broker to handle that concurrency and to maintain queues for every controller and make sure that there is a queue for every device that is in strict serial order. So it'll basically be based on which message gets to the broker first and which message the broker handles first. But the important thing to realize is that even if two conflicting sets are made to the same property on the same device, the final state of the device will be seen by every controller in the system because the final response will be broadcast back to all the controllers.
So in theory, you've got two sets of set responses if there are queues or whatever.
Yes, and there's also ways in the protocol to know which command your set response was associated with. There's sequence numbers, so you know if it was associated with a command or asynchronous. There's also a fair scheduling requirement for the broker to keep one controller from hogging all of the bandwidth to a device. The broker has to give basically fair time to every controller in the system as it accesses the device. So if one controller is sending enormous oodles of data to a device, it has to allow other controllers to get a word in edgewise, basically.
So it relies on the networking to let other fair messages through.
Well, it relies on the implementation of the broker. Yeah.
Can you jump back to slide 3 for a moment? That way everybody can see the email address again for where to send their information for.
Yeah. Sorry for the seizure here. Yes. There you go.
So again, if you need renewal credit for ETCP, here is the email address where you need to send your name, your certification number, and the magic words that you would have heard Milton say throughout the presentation. Do we have any other questions from in the room or online? I think that's pretty good. I guess everybody's waiting for us to get the standard published on the web so that everybody can download.
Everyone understands RDMnet perfectly.
Yeah, so everybody's ready to go out and implement it and use it at this point.
Yeah.
So well done. Thank you guys for presenting. And Jason, again, thank you for making the web possible and answering questions. And thanks everyone in the room for being here. With that, I guess we will conclude this webinar and we'll look forward to another one. And also that same web address, if you wish to send us suggestions for future roundtable discussions, we'd really appreciate the input. We're always looking for good topics. This looked like a really good one. We had 110 people requesting to join this, and we'd like to keep that up. So thanks everybody for being here, and we'll sign off.
Yeah.